Annuities. An annuity is a term which refers to a regular series of payments made from a fund. It is sometimes also applied to the fund from which the payments are made. One example of an annuity is a series of pension payments. Although the word annuity comes from annual, meaning yearly, in fact, the period between payments can be anything, for example, quarterly, monthly, and so on. An annuity can be for a fixed length of time, for the period of a person's life, or forever, such as an annuity is referred to as a perpetuity. Mathematically, an annuity can be treated the same way as an amortized loan, with the recipient, called the annuitant, taking the place of the financial institution, and the financial institution taking the place of the borrower. To use the amortization formula to calculate the value of the equal payments, it is important to note that the formula only applies when the first payment is one time period after the start. Alternatively, we can use geometric series and the equation of value. This is probably the better option when any complications such as increasing annual payments are involved. Sheila's accountant Mary has informed her that on the date of her retirement she will have a fund of €467,500 with which to buy a pension annuity. Sheila asks Mary to make calculations about different possible annuities. Mary finds that the AER at that time is 4.8% and bases all her calculations on this rate. In answer to Sheila's queries, calculate the following options which can be purchased with her fund. Part 1. The value of monthly payments starting on the date of her retirement and lasting for 25 years, which is 300 payments, because 25 times 12 is 300. We can start by finding the monthly rate, I, equivalent to an AER of 4.8%. Then let V equal 1 over 1 plus I, which is the common ratio. Again, this is a common device with such calculations. Okay, so we're going to start off with the compound interest formula from page 30 of the formula book, which is P equals A times 1 plus I to the power T. So we're going to start with the annual rate, which is P equals A times 1 plus 0.048, which represents the 4.8%. Next, we're going to look at the monthly rate, which is going to be P equals A times 1 plus I to the power 12. So it's to the power 12 because it's 12 months in a year, and we're trying to find out what this I is. We're going to let them equal each other, cancel out the A's. So we end up with 1 plus 0.048 equals 1 plus I to the power 12. So 1.048 equals 1 plus I to the power 12. The 12 comes over, becomes the 12th root of 1.048, and that's equal to 1 plus I. And that gives us 1.00391468 equal to 1 plus I. So bring the 1 over the equal sign, it becomes minus 1. So I is equal to 0.00391468. So this is our interest rate. Next, we're going to use the equation of value, which states that P is equal to A over 1 plus I to the power 1 plus A over 1 plus I to the power 2 plus ... A over 1 plus I to the power T. So the common ratio is 1 over 1 plus I. So if I was to multiply this first term by 1 over 1 plus I would end up with A over 1 plus I to the power 2. And if I was to multiply the second term by 1 over 1 plus I would get A over 1 plus I to the power 3, and so on. So the common ratio is 1 over 1 plus I, and that's called V. So I'm going to swap the I for 0.00391468 and 1 plus 0.00391468 gives us 1.00391468, and 1 divided by that gives us 0.9961006564. So this is V. So we take the focal date to be the date of Sheila's retirement. We let the monthly payments be A, then we use the formula for the sum of a geometric series. So we have a little table here set up that makes us see it a bit more clearly. So the first column is the payment number. So we have 1 payment, 2 payments, 3 payments, down as far as 300 payments. The next column is the amount, which we're just going to call A. And the next column is the present value. So we start off with A. Next we have A times V. Remember, V is the common ratio. Then we have AV squared, and so on, down as far as A times V to the power of 299. So we can write it out as a series. We have A plus AV plus AV squared plus AV cubed up as far as AV to the power of 299. And we let it equal to 467,500. So that's the amount that we were given in the question. So next we're going to use our series formula, which is Sn equals A times 1 minus or to the power of n all over 1 minus or. This is our series formula from page 22. So the A is the first term, which is just A. Then we have 1 minus. The or is going to be V. And the n is 300, because there's 300 payments. And that's divided by 1 minus or, which is going to be 1 minus V. And this again is equal to 467,500. So we're going to swap the V's for 0.9961006564. We got that in the previous slide. And then we solve for A. So we end up with A equals 467,500 times 1 minus 0.9961006564, all divided by 1 minus 0.9961006564 to the power of 300, and that gives us A is equal to €2,640.87. This is the value of her monthly payments, or her annuity. Alternatively, we can treat the focal date as 1 month before her retirement. Find the present value of her fund and use the amortization formula, for which I is equal to 0.003914608. So we got this from 2 slides previous. So P is going to be 467,500 divided by 1.003914608. And this is really to the power 1, but obviously we can just leave it as it is. This gives us 465,677.0569. So we're going to sub that into the formula in place of P. And we're going to let T equal 300. So both of those T's will be 300. And the I's, the 3 I's, will be 0.003914608. And into the calculator we get €2,640.87 as before. Part 2, find the value of monthly payments starting 1 month after her retirement and continuing indefinitely. We're going to let the monthly payments be A. We take the focal date to be the date of her retirement. Again, let V equal 1 over 1 plus I, which again is equal to 0.9961006564. Continuing indefinitely means continuing to infinity. Thus, we use the formula for the sum to infinity of a geometric series. So by the equation of value, we have AV plus AV squared plus AV cubed plus ... forever, and that's equal to 467,500. We can factorize, we get A times V plus V squared plus V cubed plus ... going on to infinity, again is equal to 467,500. So by the formula for the sum of an infinite geometric series, which is this formula here, A over 1 minus or, from page 22 of the formula book. So we're going to let A equal V and or equal V. So we swap S infinity for 467,500. We swap the A for V. 1 minus or becomes 1 minus V. And this is all multiplied by A, because remember A was the common factor. Both V's get swapped for 0.9961006564. This gives us A is equal to 467,500 divided by this, which gives us A is equal to €1,830.08. Bonds. A bond is a certificate issued by a government or a public company promising to repay the borrowed money on a fixed date, along with interest repayments at fixed intervals. A bond is a negotiable security in that it can be bought and sold. The issuer of the bond owes money to whoever holds the bond on dates when the money is due. The conditions attaching to bonds can differ greatly. The equation of value can be used to evaluate a bond at any stage. So remember, this is the equation of value. The rate of interest involved in any given transaction, the value at any time of all the payments made by one party to the transaction, and the value at the same time of all the payments that the party will receive must be equal. So what that means is the key principle behind financial transactions such as these is that the sum of the equivalent values of all advances or borrowings at any focal date is equal to the sum of the equivalent values of all repayments at the same focal date at the going rate of interest. Example 4. A company wishes to raise finance to expand their operations. To do so, they issue a number of 10-year, €10,000 bonds that will pay €200 at the end of every 6 months, up to and including the maturity date. If the current market interest rate is 4.5% per annum, what is a fair market value of one of these bonds? We will work the question with a time unit of 6 months. Thus, we have to find the interest rate for 6 months that is equivalent to an annual rate of 4.5%. So again, we're going to use the compound interest formula from page 30, which is P is equal to A times 1 plus I to the power T. So we're going to let I be the equivalent interest rate for 6 months. Then we get the annual rate is P equals A times 1 plus 0.45, so it's the 4.5%. And the 6-month rate is going to be P equals A plus I to the power of 2, because 2 times 6 is 12 months, which is a year. We're going to let them equal each other and cancel out the A's. So we're left with 1.045 equals 1 plus I squared. We're going to bring the squared over the equal sign, so we get the square root of 1.045, and bring the 1 over the equal sign, it becomes minus 1. So I is equal to 0.02225241501. Then using the equation of value, P is going to be equal to A over 1 plus I to the power 1 plus A over 1 plus I to the power 2 plus, up as far as A over 1 plus I to the power T. So V is going to be our common ratio, which is 1 over 1 plus I. So basically, if I multiply the first term by 1 over 1 plus I get the second term. If I multiply the second term by 1 over 1 plus I get the third term, and so on. So this is our common ratio. So I'm going to swap the I for 0.0222524151, which is what I got up here. And 1 divided by 1 plus this gives me 0.9782319761. So a fair market value for one of these bonds is the present value of all future payments to be received. The present value of the €10,000 to be paid in 10 years is 10,000 divided by 1.045 to the power 10, which gives us 6,439.27682. So I got this from this formula. So I know I'm discounting backwards, so I have to divide. So I use this formula where P is equal to A, which is the 10,000, divided by 1 plus I being the 4.5%, to the power of T, which is the 10 years. I'm going to let P1, P2, up as far as P20 be the present values of each of the 6 monthly payments. Remember, 10 times 2 equals 20 payments. 10 years times 2, because it's 6 months, there's 2 6-month periods in a year, gives us 20 payments altogether in the 10 years. So P1 can be rewritten as 200V. Remember, 200 is how much you're going to pay every 6 months, and V is the common ratio. P2 can be written as 200V squared. P3 can be written as 200V cubed, and so on, up as far as P20, which can be rewritten as 200V to the power 20. So now we have our series. Now what we want to do is use our series formula from page 22, which is Sn equals A times 1 minus R to the power of n divided by 1 minus R. So our A is going to be 200V. That's going to be multiplied by 1 minus R, so 1 minus V, because R is V, to the power of N, so to the power of 20, all divided by 1 minus R, so all divided by 1 minus V. So we need to swap the 3 V's for 0.9782319761, which we got from the previous slide. And then we basically just put all of this into the calculator and we end up with 3,200.302,689. Thus, a fair market value is this plus this, which is €9,639.58.